Okay, continuing on with discussion of the experiment 11, we're reached now basically page 135 of your lab manual. And so here what we need to do is really begin to discuss what data you're going to take if you were in the laboratory and how you use that data. Now I'll provide the actual data points that you'll use to analyze to calculate the wavelengths for the spectral lines of hydrogen and the spectral lines of helium. And on the Canvas website for the laboratory class for experiment 11, I've included some videos, or really a video of me performing the experiment and how the experiment setup is. You can see the gas discharge tube, the fixture that they go into. The two rulers that we use, they're cross rulers, a long one with a smaller cross one, and basically the measurements you need to make. In addition to those, I show you just what the gas discharge tubes look like when either hydrogen or helium are in there and it's turned on. Then I have included also a picture of some of the spectral lines that you can see through the diffraction grating, so you get a sense of what they would look like. And then finally, there's the actual data taken by me and another adjunct professor of that for the gases of hydrogen and helium, and that's what you'll use in your analysis. You find that all online. So you've answered basically down to the middle of page 135, and then what we see is the setup, and the setup is such that there's the gas discharge tube right here, holding the gases right there, and that's lit up. It's set right next to a long ruler, and then there's a cross ruler. And right here would be where the diffraction grating is located. And you would look right there, right behind it down to look and find the spectral lines and where they line up onto the small cross ruler. Now, if you look at that drawing, what you'll see is that that there's a distance y. And the distance y is from the diffraction grating over to where the small cross ruler is at, the smaller of the two rulers. And that is your distance y. And so basically what you're doing is you're moving the diffraction grating back and forth, looking through it with the tube turned on. And what you'll see is that the outer diffraction lines, or the spectral lines, are moving in and out along the little ruler right here. And what you want to do is position this so you have the outer spectral lines as far out as possible before they fall off the ruler. And so what you discover is that when you look through this, and if you've done it correctly, let's say that this is hydrogen in here, to keep it as simple as possible. You would find further out would be the spectral lines, and remember you have the primary ones on either side of looking straight through there. So you have them positioned, you pull this out and in enough to get those red spectral lines to be right at the very edge of that small cross ruler. And then you'd find an aquamarine on either side, and then you'd find a violet. And they're very pretty colors. I really wish you could have seen it right there. So it turns out then on page 135, you would measure your position y for both hydrogen and helium. Again, that's found within experiment 11 on your Canvas site. Then what you have is your distance out here to any particular spectral line, measured from the center of the small ruler out, is X1, let's say, and X2 for, let's say, red. So for each spectral line, you have two measurements of X. So there's two measurements of X for the red for hydrogen, two for the aquamarine for hydrogen, two for the violet of hydrogen. And you would record that. Then you would remove the tube, replace it with the tube filled with helium, move the diffraction grating back and forth until you can get the spectral line spread out to be still falling on the small cross ruler, but not going off. And then you would remeasure X for helium red, X1 and X2 for helium orange, X1, X2 for helium green, X1, X2 for helium violet. And remember this, the shades of red, green, and violet for helium are not the same shade of red, green, violet for hydrogen. That means their wavelengths are slightly different, and you'd expect that. So going to the next page in your book, then you would have filled out tables 1 and 2 with those distances, D, X1, X2 for all the different spectral lines. So table 1, when you look at this, has to do with basically helium. Table 2 is for hydrogen. So that's provided to you. Again, look on the Canvas site. You'll find that data within Experimental 11. You still have one task to do there, and that is to average the values of X1, X2 for each spectral lines. Hey guys, how do you average two numbers? You add them together, divide by 2. Excuse me. So you'll find a average distance X1 and of X1, X2 for red of helium, and then for orange, and then green and violet for helium, and then for hydrogen, you do it for its red, its violet, and its aquamarine. And so you'll find basically seven average values for X for each spectral line for the two gases. Now, we go through, and I'll work with you on the analysis and walk through the remaining part of page 136 and then 137. And then you'll be finished with this lab, except for one more thing. Once you publish this and finish up this lab and give it to me, I'm grading. You don't know how fast I'm trying to grade to get everything done for both the lecture and lab class. But then you just prepare for midterm number 2. And that will be, again, next Monday, which I think is the 17th, if I remember correctly. And so what we have here, we go back to the diffraction grating. So here's your diffraction grating. Here's the lines in here. And every diffraction grating, you're given how many lines per millimeter. And so for this particular one, it's 536 scribed lines for every millimeter. And so looking at this, that is your N1 value. So you can just write that down where it says N1 equals the number of lines per millimeter, right below tables 1 and 2. And then we want to know what N is, which is the number of lines per meter. Remember, 1 meter equals 1,000 millimeters. So, N is simply equal then to 1,000 millimeters per 1 meter times N1. And so what that'll give you then is the number of lines per meter, which is what you want. So simply you're multiplying by 1,000 N1. You can see that. Okay? And then finally, we're interested to know what the distance is between the lines. And well, if we know that there's this many lines in a meter, then D is simply going to be equal, as it shows there, 1 over N. Just the inverse of that value there. A very small number. Now, how is this used? Well, it's based upon what's right below the two tables, Table 1 and Table 2, and it's also shown more in a symbolic way on the top of page 137. The wavelength of any spectral line, if you look at this, the distance between two lines on a diffraction grating is equal to, well, guess what? Your average value of x divided by your y. It's basically a geometric orientation that you can find this relationship. And we'll leave it just as a given thing to you. So in other words, this tells me I can calculate the wavelength. Wavelength is simply equal to, again, x times the distance d, that's the average value of your distance x along the small ruler of any particular spectral line, divided by y, which you have already measured. All this data is given to you. And so that's how you would do this. Now the actual pragmatic way to do this is this. Lambda, remember that d is just 1 over n. It's simply your average value, I'll put that down explicitly, of x for any spectral line, divided by the wavelength, by the distance y for hydrogen spectral lines, or helium for helium spectral lines, times n. N's always a given. And what you'll end up with is the wavelength in terms of meters. Okay, which is going to be a very, very small number, which is something you don't particularly want to do. And so we remember that what we have here, 1 nanometer is equal to 1 times 10 to the minus 9 meters. So simply what you're going to do then is, once you have this value here, simply divide it by 1 times 10 to the minus 9. And what that gives you then is the answer in terms of nanometers, which is what we want this in terms of. And so don't make this hard. So let's just double check how we're doing this. Number one, you get all this information. You find out what n is. So this is step number 1. Find your n value. Step number 2, find your wavelength in terms of meters. It's going to be a very small number, okay? And then finally, step number 3, divide that small number there by 1 times 10 to the minus 9. And that'll give it in terms of nanometers. And then you'll do this for each one of the spectral lines. So you're going to do this 7 times. And then you'll put your number of nanometers in tables 3 and 4 for helium and then for hydrogen. And right next to the measured values that you've got here that you're going to come up with, you'll have the accepted values. As an example, if you look at table 3, red, the accepted wavelength is 668 nanometers. So if you're getting something really weird that says you've made an error in your calculations, go back to what I've said to do. Number 1, you know what n is. It's 536 lines per millimeter. Got that right there. That's what that is. You have that value times 1,000 millimeters per meter, and that'll give the number of lines per meter. So simply take that and multiply it by 1,000. Big number. That's 1. Number 2, take your average value, divide it by your y value for the gas you're using, equals, and then divided by n equals. And that should give you a small number in terms of meters. Step number 3, to convert that to nanometers, simply divide by 1 times 10 to the minus 9, and that should get you the number that you want in terms of hundreds of nanometers. Around to a whole number. Don't worry about decimals with this. And then the final thing you do is you find the percent error. Percent error is shown below. You take your accepted value, take your accepted value, subtract out your measured value, the experimental value is what I call it there. I should have kept it the same value. Something I'll probably change in a correction to this. So it's your percent error is the absolute value of your accepted value of wavelength minus, I'm going to just use the terms that you have here, of your measured value or experimental value. So this will always be a positive number. So if you get a negative number, just strip off the negative and then divide this by your accepted value again times 100, and that'll be your percent error. And you'll be surprised just how good that is. And then explain what percent error is. Remember what that is. It is a comparison of a measured or experimental value as compared to a true accepted value of a quantity. So we know what the true values are of the wavelengths. That's given in tables 3 and 4. You have your measured values and calculated values of your wavelengths for each spectral lines. That's the measured or experimental value. And so that's what you're doing. And then just on the conclusion there, how do your values compare experimentally to the true values? And you want that percent error to be as small as possible. It won't be 0 though. There'll be some error in this. That's always something to be expected. And so, this is what someone does. When you study the spectra of stars, one thing you can do is you can just look at the stars first off with the light, or whatever you're looking at. The light will tell us that it's there. But then you spread the light out using diffraction grating at an observatory, and then you begin looking at the spectral lines. And with the spectral lines, then what you do is you verify which gases would produce the specific spectral lines you're seeing in a star's spectra, or spectrum, excuse me. And so this gives a chemical analysis of the makeup of stars and other objects in the heavens, and that's really a useful thing. And understand, the diffraction gratings I used are cheap. They're only $1 or $2. The diffraction gratings used by at an observatory are made very, very precisely. And so because of that, they can be extremely expensive. They can be in the realm of $10,000 or even much greater because they're so optically made perfect. The reason why we take 2 values of X is that because everything's not real precise, by taking the average of 2 values of that X direction that we measure for each spectral line, we can decrease the error. So it gives us a little bit better experimental result. So, I'm watching for comments and questions. I think we'll have maybe on Friday. Well, let me know. Give me some emails and let me know if you'd like to have a little office hour to discuss anything going on with having troubles with these measurements. Let me help you. Okay, guys, so this is the last lecture on the last experiment for spring 2020. What a weird time this has been, right? So I want to remind you on Monday, let me double check the date because it's awfully hard to remember what the heck's going on here. On Monday, it's actually Monday the 18th of May. The experiment is due. On the 18th, we'll have the lab midterm number 2, starting at 3 o'clock, going till 7, which will finish up all of the what we need to do for this semester for the laboratory 117 astronomy. I'm grading. I'm going to add a lot more grades over the next couple of days to the spreadsheet. Once I have more of the experiments graded, I'll update the spreadsheet with your grade, and I'll go ahead and place that information, another copy of the spreadsheet, grade spreadsheet, on Canvas. So that'll come to you soon. And my hopes is that very early of next week, I will proceed and get your grades posted, final grades posted for the semester for this lab. So I'm hoping Wednesday, Thursday of next week we'll be finished with this. So anyway, guys, I hope this is clear, and I'm here if you need me. Take care. Go ahead and turn this thing off. If I get my mouse to work. Well, take care. Talk with you soon.